Hello and welcome to the 10th lecture of the course. And this topic of this lecture is a design consideration for hydrodynamic lubrication system. We have already learned from previous lectures that hydrodynamic lubrication aims to minimize friction and wear, particularly in machines where we are utilizing some relatively moving components or relatively moving surfaces. This form of the lubrication is especially crucial in situation particularly where the high speed is involved. Maybe say we can say the 10,000 rpm plus, or maybe say in meters 10 meter per second plus. Fundamental concept of underlying hydrodynamic lubrication is the creation of the lubricant layer that bears the main load, which is the load coming on the bearing surface, and prevents the direct contact between metal surfaces. The lubricant is delivered to the contact area using some techniques. It can be oil pump, it can be splash lubrication, it can be wick lubrication. However, in my view, the oil pumps are commonly employed to enable the recirculation of the lubricant. Performance of hydrodynamic lubrication is commonly categorized, or maybe say characterized, by the Reynolds equation. We generally go ahead with the one dimensional Reynolds equation, two dimensional Reynolds equation, Reynolds equation for non-Newtonian fluid, Reynolds equation plus thermal equation, Reynolds equation plus elastic equation plus thermal equations. This equation considers basically viscosity of the lubricant, velocity of the surfaces, and on top of that, the geometry of the lubricant components. The configuration of bearing surfaces is main feature or the pivotal in the creation and sustenance of the lubricant film. Hydrogen lubrication is a widespread in number of applications: engine, gearbox, turbine, and any other rotating machineries. So this is what we have already learned, but what we have learned categorically, particularly from previous lecture, is something like hydrodynamic lubrication generates a pressure in relatively moving inclined surfaces. And one better thing is that this inclination comes its own. Let's take it, this is a journal that has been shown. This is a journal surface, and this is a bearing surface or sleeve. And here, relatively moving component, that's a velocity or angular velocity is omega. So this taper angle or this convergence has come its own. Initially, it will be vertically down. The shaft will be something like bearing center here. The shaft center will be somewhere here, vertically down. And even in starting, it will move against this because fluid, there will be some sort of resistance, and OJ will turn out to be here. But in a steady state condition, OJ turns out to be this side, and this is what we call a stable condition. So what we can say here, the journal bearing is, it can be partial journal bearing also. However, mostly we use, particularly when there is a need of recirculation of the lubricant. This is a cylindrical structure that surrounds a spinning shaft, and here what we are seeing, the spinning shaft and the journal are the same thing. The journal surface and the spinning shaft is the same machine components. It supports a radial load, or sometime it acts only the guide. The main purpose is to act so the relatively smooth motion goes, or transmission of torque goes on. Now coming to the steady state condition, particularly as I mentioned that here this is the OB, center of the journal bearing, and OJ is the journal of the center of journal. Once this becomes a steady condition, then journal assumes a position within a bearing sleeve. Of course, we can say this position can be defined with the coordinates. And what are those coordinates? We are using radial coordinates. In this case, we have eccentricity ratio or eccentricity and attitude angle. So there is eccentricity. We already know the eccentricity itself is a gap between the journal center and bearing center. And that's why we are writing here eccentricity is a separating journal center OJ from a sleeve center OB. So this is the gap. Now, if those both the centers becomes a concentric, then eccentricity will be 0 and load carrying capacity of the journal bearing becomes a 0. However, if it is equal the radial clearance, this E is equal to radial clearance, if I say, then in the situation it will have a maximum load carrying capacity, but there will be metal to metal contact and hydrodynamic lubrication will not be there. So what we mentioned last time, E is basically, if I E by C R, if I assume is a normalization, then this should be approximately 0.8, and that's what we use, 0.8, and of course it should not be lesser than 0.5, or if this ratio is, we say with epsilon, we say epsilon should not be lesser than 5, we should not be there, it should not assume this manner. Epsilon should not be greater than zero point 0.9. If it is more than 0.9, again there is chances of eccentricity when the general surface is touching the bearing surface. Another one, we use the word attitude angle, and what is attitude angle? We say angle formed by the load line and a line of center. So this is the line of center. If you look at this line, this is the line of centers. Reason being that it is joining the OB and OJ. So this is called a line of center. That's what has been written here, line of center. And then load line. This is the load line. Whatever the angle between these two, it will be known as attitude angle, and that makes a coordinate of on the general position. We say with a greater lubricant viscosity, if you increase the lubricant viscosity or increase the speed, then what will happen? Eccentricity will be reduced. So if there is eccentricity 0.6, and then you suddenly increase the RPM omega here, maybe say instead of 250 RPS to 300 RPS, then there is a possibility that eccentricity will come down and eccentricity may become 0.55, 0.56, something like that. There is a possibility, and as eccentricity reduces, attitude angle will increase. In last lecture also we mentioned attitude angle should not be greater than, or maybe say always should be lesser than 45 degree. That's what we want, attitude angle should be lesser than 45 degree, that will be advisable. Now let me indicate again here, the once the channel and the channel occupies a steady position, we will be able to get a thick lubrication. However, there is always an issue. We say high friction coefficient and mild wear during startup and end process, that means a transient process, as well as this is one of the drawback. Another thing is that we continuously require a lubricant if there is a pump failure even for the few seconds, or if a pump is not supplying a lubricant to the bearing, then bearing will stop working. So it is not like a rolling element bearing or grease lubricated bearing, even the delay of a supply of lubricant will not affect that much. But in the hydrodynamic bearing, it is very necessary that pump should work continuously. If it is gravity feed, again in that situation the pump, there should not be blockage. So what we are saying, the recirculation, that, and whenever there is a recirculation, again there is a need of the cooling the lubricant oil also. So this is very important. Now we see the lubricant oil will also require a complete lubrication system. And what is the lubrication system? There should be pump, there should be filter system, there should be tubing, and maybe valve mechanisms also. So these are the major drawbacks. However, one drawback, particularly high friction and the mild wear, can be overcome if we are able to provide this kind of boundary lubricant layer. That is what we studied earlier in previous lecture, maybe lecture 8. And then what we say here, incorporating additives, it can be physical adsorption or chemical absorption. So we are writing fatty acids or chemical agent into lubricant. We mix with a lubricant so that the thin protective film is formed on the surface. So I'm assuming that there is a surface 1, and then this is a lubricant or protective lubricant on this. This is the surface 2, it has a lubricant layer on this. So this is what we require, particularly when we want to minimize the friction and wear even in transient situation. So in ideal situation, or maybe it's an actual situation, we require a liquid lubricant, but additives should be mixed. Physical adsorption or chemical absorption should happen so that surfaces are protective even in transient conditions. Now, why we are talking about hydrodynamic bearings or hydrodynamic lubrication mechanism? Now, one major point comes, it is a self-acting. What is the meaning of self-acting? If the load is increases, the general position changes its own. if speed increases, general position changes its own. So it is very effective. We are not really regulating general surface from that point of view, or maybe we are not controlling completely, even though we know that we can really go ahead with active control, but here actual control happens its own. That's why the name has been mentioned as a self-acting general bearing. And this is can be utilized for the steam turbines, centrifugal compressor, pumps, motors, even big size motor, they can use general bearing configurations. And then major thing for the advantages coming is something like it has a very high damping ratio. Reason being is a liquid, and then it damps if the damping coefficient is on higher side, and then it does virtually doesn't have a wear, so it can go for much longer service life. Its durability is on the higher side, and it provides a minimum friction. Even the friction coefficient, what we say 0.025, 0.001, is possible using this kind of bearing. So this is very important. What else we have learned, that whenever we go for the bearing selection, we have a number of bearings. One is called a rubbing bearing, or sometimes we call a stout bearing, or sometimes we call it a grease lubricated bearing. Other one is a rolling bearing, and we can really think about a porous bearing, which is impregnated with a liquid lubricant also, or maybe lubricant additives along with that. We are discussing something like a hydrodynamic bearing or hydrodynamic oil bearing. We do have other bearing where we call aerodynamic plus aerostatic bearing. And then every time we really require to consider which bearing is very good option for us. Now here why we are using word aerostatic or aerodynamic bearing, reason being the viscosity of oil to viscosity of the air is a ratio is very high, it may be many times greater than 100. That means if we want to really reduce the coefficient of friction or friction loss to 1%, better we shift to the air lubrication. But when we talk about air lubrication, manufacturing accuracy has to go much higher side, and that's why we say when RPM is very high, then only this kind of bearings will be required. Another point, the load carrying capacity of this bearing is almost negligible. That means very high speed only, then we can think about this kind of a bearing. Otherwise we should not think about a aerostatic or aerodynamic bearing. Of course there is a some sort of limit has been shown as the busting limit. Beyond this RPM, this the shaft will burst. Of course this is a subjective, because we are continuously updating materials also, processes also. And another thing is that this is mentioned on RPM. In actual case it has to be velocity, it's not a RPM, because in velocity we have a radius also. So without counting the radius, we can't give this kind of curve. So these are the picked up from a literature. I'm just trying to brief about this. There is a bearing selection way, and then we can choose a bearing appropriately. Now what has been learned from here, that many times a bearing is being selected, and in this case particularly we have not defined a radius. So ideally we should use a word dn. Dn is a RPM, and the diameter, that means diameter of the shaft journal, and n is RPM. So we consider a dimension also, and rotational speed, or basically velocity. And now this limit has come because of the dissipation of heat. If whatever the heat is generated, it is not removed from interface, then heat will get accumulated, and temperature rise will always be on a higher side, and it will turn out to be unsteady situation. And we want steady situation, then we need to remove the heat. So that's why the limit has been mentioned here as a 1 lakh and the DN number for hydrostatic plus hydrodynamic bearing. For aerostatic and aerodynamic bearing, again it's a 4 lakh or 400,000, and magnetic bearing it has been mentioned as a 450,000. Again these are the only the numbers which keep changing with time. Maybe every 10 years this number increases. An interesting thing is that if you look at Niels tribology handbook, which I have referred a couple of times, and they have mentioned that if I'm using a rolling element bearing, that even with a grease, this DN number can go up to 300,000 to 350,000 just with a grease lubricant. Coming to the oil, this number can go 450,000 to 500,000. That's a huge number. That means it is exceeding even the magnetic bearing. So this is way continuously when we are updating the technology, we should also keep changing these numbers. That's why we say data driven approach makes much more sense, because we are continuously updating our knowledge. So whatever is written something like in 1980 and this comes to the 2000, naturally there is already variation. So within 20 years technology has upgraded in a significantly higher level. Now another thing is comes that when you are trying to solve the bearing design problems, you need to solve number of partial differential equations or equations. And in last lecture we learned something like a short bearing approximation. That means we assume that pressure distribution is happening or is developing or is a more dominant and only in one direction. But of course this is inaccurate. It's not completely accurate, but it gives a understanding about the system. Accuracy is different, precision is different, but understanding the system, how the system is really working. If we don't want inaccurate results, then we need to solve the pressure equation, the distribution using the partial differential equations, and that too again incorporating all the factors. That means there should be a viscosity thinning effect, that means temperature rise will be accounted. Another one is that the pressure viscosity in the increase because of the pressure, so that is also important. So what we say, the calculate important design characteristics, the load capacity, and in the last lecture also we mentioned that general bearing is basically inverse problem. Here the load capacity will be given as an input and we need to find out what are the coordinates of the journal. So it is an inverse problem and we need to do a iterative scheme for that. So here what we are saying, the important design parameter or characteristics of the load capacity, maximum pressure. This also maximum pressure limit comes because of the pressure the strength of material, and most often we say the strength of material is a 10 can sustain up to 10 megapascal, 20 megapascal. Different materials, actually this limit will change. Another one, that the flow, how much flow really we require, because we have a pump and we really require a pumping source, which we need to define how much is the flow rate, how much will be the power loss, as low as possible, that will be the important for us. And then what will be the temperature rise. So we want a minimum to minimum temperature rise in a oil film, so the steady state condition remains for the longer time without disturbing it. So these are the important aspects. Now coming to the high RPM, as I mentioned, aerostatic plus aerodynamic bearing are more important. So this is what I said, the one sketch has been shown. You can see here cylindrical aerodynamic bearing. It's the same the way hydrostatic or aerodynamic bearing, liquid lubricated bearings are there. Then again the line up center, this is again attitude angle here, and then this is again eccentricity. So values are more or less same, only here we are using the gas film, we are not using the liquid film. Now in gas film we cannot use additives. So in the situation what we do, we always mix with the aerostatic. That means we use a compressor to pump initially pressure and levitate the journal, and that has been shown a kind of a thrust option here. You can see here the sharp surface is or maybe say supporting surface has been levitated by aerostatic pressure, and then there can be a number of groove arrangement to levitate the shaft. So aerodynamic aerostatic bearings are more or less like hydrodynamic bearings. So only thing in this situation, we really need to talk about discuss about the density, because density of the air or gas also increases with increase in the pressure. So one more level of difficulty will come when we are talking about aerodynamic plus aerostatic bearing, and really require little more computational power to solve this kind of equations. Now I'll just cover a couple of case studies. One of my research paper which was published in 1997, what we did in this case, as you understanding that there are a lot of design related issues for the hydrodynamic bearing, and many people are incorporating some sort of design charts, and they have to really require a few at least 5 to 10 charts to solve the problem. That's why we have given main theme as a design table. And why we have given to assist the designer who are not very much interested into the numerical and mathematical like complications, and then they want to see the formula, algebraic formula, and then they want to do some sort of coding. It can be a simple hand calculator also, with codable computer calculator also. So what was measures? We say that to analyze the performance of journal bearing, generally there are two approaches: solving partial differential equation. Second thing is that going ahead with a completely one-dimensional approximation, like a short bearing approximation, or going for the design charts. And we felt that both have some sort of restriction. So why not we go ahead with a hybrid approach? So hybrid approach is basically we are incorporating some sort of we say numerical approaches and some sort of analytical approaches, and we're combining to predict the accurate results, and then which can be compared. So we are just showing the accuracy of this. You can see here this is what we call a length to diameter ratio, L by D ratio, and then as the length is increases, the length compared to diameter increases, short bearing approximation will turn out to be invalid. Short bearing approximation is easy to calculate the pressure, and we are say often the short bearing approximation, if then this L by D ratio is more than 0.2 or 0.25, should not be utilized. So we have given both the cases 0.25 and 1. We have compared one Reason-Narang method as they combine short bearing and long bearing approximation. We have used completely FEM method, the finite element method, and this is a present with the paper presentation or design table approach has been given. So it has been covered from 0.1 eccentricity to 0.99 eccentricity. Of course, we know that this portion should not be utilized. Of course, this is only for the comparison purpose, but for design purpose this should not be utilized. For design purpose this should not be utilized. So if you are going for more than 0.9 eccentricity ratio, we assume that we are not going for the right design, because accidental cases, those things cannot be handled easily. So we try to restrict from more than 0.5 eccentricity ratio to zero point 0.9, or maybe 0.8 will be the kind of optimum initially. So this is what we really require. And what is the design table? In a paper it has been given as a table 3 design table. It has a total 21 steps to simplify and then to rearrange in a manner so that we require a minimum to minimum iteration. So it has been arranged in number of steps, where we say that the step 1 to 7 is basically required to calculate how much flow is really required, how much will be leakage, and what will be the location of maximum pressure. So this is a what location of maximum pressure can be calculated using these formulas, or maybe say 6 complete formula has been given here. Leakage can be calculated or recirculation can be calculated based on this formula. So 1 to 7 is basically for that purpose. Now coming to the step 10 and 11, we are saying that to evaluate the load carrying capacity, we need to integrate this portion, or this we need to utilize the step 10 and 11. Just to simplify, we have used a 7 step consideration, or 6 step you can say, where the step size has been mentioned as a b minus a divided by 6. This is upper limit and this is the lower limit. Now sometime we can say a is equal to 0 and b is equal to pi. That's a approximation. And sometimes we say b plus alpha. It can be 10 degree, it can be 20 degree, it can be 30 degree. Whatever and when we say step size, so this y1 is basically ya and y7 is basically yb, and then in between we really require these steps to be utilized, a plus kind of thing. In this case it will be a plus, when we say the y2, it will be a b minus a divided by 6, and then as y3 it will be multiplied by 2, y4 it will multiply by 3, something like that. Now one major issue comes in when we are solving the bearing. problem is viscosity and temperature dependence. And in previous lecture we took this example how to calculate the pressure as a viscosity and the temperature relation. We simplify, we say that one of the temperature can be utilized to give as a one of the constant value. That's here we show that last time as a eta 60. That means if you choose a temperature 60 degree, we can use a eta 60, and then whatever the temperature, you subtract that value of that. If it is a eta 30, I'll write down eta 30 and this will be 30. If eta 40, it will be here 40 degree. So here only we have only one constant, that's a B constant, which needs to be evaluated. That's what we learned in previous lecture. Similar here, it has been mentioned here. You write a little more refined manner. We say eta effective. Here we were talking about the only temperature which have been given. So that value of the B, or in this case particularly beta, can be calculated. But when we are trying to use in expressions, particularly design table, where we do not know temperature at all in beginning, so we need to give this expression. So eta and at the inlet temperature, whatever the 30, 40, 50, whatever we define, we will write down that. And then here the beta can be calculated based on the 3 viscosity value, 4 viscosity value. You can use any curved method to figure out the values. And then once we utilize this, particularly you can see here 16 and 17. So intelligently it has been mentioned in a manner, we don't really require iteration up to this. We require iteration only in these two steps, because whatever the delta the T temperature rise and viscosity, as the temperature increases, the delta T increases, viscosity will reduce, and then this iteration will come up finally what will be the T factor. Just two steps, iterate and the results are fine. Earlier most of the method which have been utilized, they had to involve all the steps for this iteration. For in this design table we required only 2 steps, and that much faster compared to any other method. So this is what has been utilized. Once the effective temperature has been determined, effective viscosities can be calculated. Then we have a step 18 to 21 to calculate a load capacity, friction force, max temperature, and max pressure. However, as earlier also mentioned, that eccentricity is not given as input, load is given in input. So we really require to iterate. That's why this design table turned out to be very useful, because it takes much lesser time to iterate compared to numerical method, and accuracies are really very good. So we took 2 case studies in that paper to establish whether the whatever the approach we are choosing is correct or not. So first case, these are the results which are already published. So we took a length as a 70 mm, L by D 0.7. Here the R by C, generally we choose R by C as a 1000, but here the R by C has been selected as 636. As I say that these are the established results people have published, so we wanted to just compare with those results. You can see here the clearance has been selected on a higher side. Now beta has been already defined, thermal properties have been given, applied load, temperature, viscosity, supply pressure. Now one more thing has been given, there is an axial groove 10 degree which is extending circumferentially, and the length is 60 mm. And this diagram was shown in a previous lecture. We say that in even hydrodynamic bearing, this portion is a conversion post which will have a full film. But here we know that divergent portion, this is completely divergent portion. In divergent portion, available liquid is not that much, and the fluid or liquid cannot sustain negative pressure. That's why that there will be formation of air cavities and what we call as the liquid streamers. That is what will come out, and this is where the we can feed the lubricant. That means if I have to make a oil hole, I will choose this location. If I had to make a oil hole with a complete circumferential groove, which is a kind of the engine bearings, if there is a circumferential grooves, then I will make in this manner. Now, of course, when we have a circumferential groove, then effectively we are dividing one bearing into two bearings. So there is a groove in between, and this is a one bearing, and this is a another bearing. So this is effective. We are doing an engine bearing. We do one of the, like particularly in Minecraft shaft bearing, we do this kind of thing. Now in present case, what has been given, this theta minus 4, theta 4 minus theta 3 has been given as a 10 degree. That means circumferential angle is 10 degree, and the length, if I see using this as a complete one length, that means this length has not been selected. The length maybe say 5 mm from this side and 5 mm from this side has been selected, the length of the groove. Why we are not using the through and through groove? Because whole liquid will pass or will be moved out. It will not get recirculated. It will not be supplied to this zone. So this is the reason why we don't want the groove to be through and through, and we restrict at the ends. And this is a very important step to think that whenever we have a length like in a 70 mm, we are keeping a 60 mm as a length, or maybe 45 mm as a length. Of course, it can be designed, but it cannot be 70 mm. Now, we compare the results with established result. We use and then an experimental results which were published earlier. This is what we call a thermohydrodynamic lubrication. There's another solution we call isothermal and ADI case. What is the meaning of this? In this case, particularly shaft rotates, it carries a lubricant layer. So that's why it is maintained as a isothermal case. While a bearing doesn't really release energy that much. So again, that is called ADI solutions. So that's why this is a combination. The shaft is isothermalic condition and bearing as a ADI condition. And this is the simplest one. Most of the book and most of the initial paper, they were based on isothermal analysis. They will figure out what will be the effective temperature of the sum, and then they will measure this one, and then they will calculate the viscosity, and then they will present the results. So it has been shown here. One thing is a eccentricity as a 0.452. Now, of course, experiment we cannot find out this value. Reason being the applied load is being given. So we need to do iteration to match it, and then matching in all three cases has been all four cases have been shown. In our case, 0.452 TSD solution, which is TSD solution, which is a very good solution. It gives a similar value. The only drawback about the TSD solution is that it's a numerical solution and it requires a more computational power. And of course, other parameter, friction force, maximum temperature, lubricant leakage, Sommerfeld number, attitude angle has been given in this case. Now, what are the major issues? We see, even though we have compared these results with established results, but when I am thinking from a designer point of view, I will see that here RPM is on a hard side. That means we really require a liquid lubricated bearing. But this eccentricity is 0.452, something lesser than zero point 0.5. If I can increase eccentricity, it will turn out to be very good. Similarly, if I can reduce attitude angle, it will be more favorable. So this is what the initial case comes that we really require, and main thing comes if I can really reduce the clearance. If you reduce the clearance, naturally there will be some impact. But we know very well that from previous lecture that if I reduce the clearance, my load carrying capacity will increase. If I reduce this clearance, that means whatever eccentricity ratio we are getting 0.5452, it may turn out to be zero point 0.4, further reduction in that. And then what we selected, we recommended R by C as 1,000, and then this is a factor has been given, and this factor comes out to be somewhere here 1.57. So if I reducing to 1, load carrying capacity is increasing and eccentricity ratio will further come down, attitude angle will reduce. So this is not a right option to reduce the clearance. Second option comes go for the grease lubricated bearing. Reason being, these are the partial bearings, and it will not have a complete circumference, or the grease will not be spread over a whole circumference. It is not going to really support a lot. But only the problem, as I mentioned, the velocity is more than 10 meter per second. which is somewhat problematic. When what is the advantage and what are the disadvantage of the grease lubricated bearing? Because here this is only one slide I'm covering. Of course, I'm giving a reference that the most detail has been given in the tribology handbook. How do we really design grease lubricated bearing? We are not talking about hydrodynamic grease lubricated bearing, and it is always known as a starved lubrication. It will not have a continuous lubrication, it's a start lubrication, and it will have only the partial film. It will not have a complete the shaft as a surface film. There's a possibility that eccentricity will increase in this case, but in the situation also we need to maintain a surface finish of journal and bearing. Otherwise, there will be more and more aspirative contact and the coefficient of friction will increase. If we want to maintain the low coefficient of friction, then again we need to revert back to the hydrodynamic lubrication. Now, this particularly the figure which has come up from which we took from a tribology handbook, it says very clearly if the this grease lubrication if the operating speed is a 10 meter per second or more than that, we cannot use, and we really required a lubrication area which is for hydrodynamic or maybe hydrostatic kind of mechanism. So we cannot use this one, and then only the advantage of the grease lubricated bearing will be we will not require a pumping mechanism, we will not require a filter system, we will not require the tubing. So complexity will come down significantly, and then only coefficient of friction will increase. Sometimes we say coefficient of friction which increase because of grease lubrication. We should equate with the power of the pump. If I'm using pump and filter system, and the pump power is whatever the pump requires, if I mention in terms of the coefficient of friction, if that is more than the grease lubricated than the bearing friction, then we should go back to the grease lubricated bearing. So this is only power, but we are not talking about the wear. Quite possible the grease lubricated bearing will worn out faster compared to liquid lubricant. So for that purpose, that's why we are mentioning the surface finish of journal and bearing needs to be very good, so the abrasive wear can be minimized as low as possible. So I consider two things. One is the clearance. Here, reduction in the clearance is not that advisable. Second, grease lubricated bearings, again because the velocity is higher side, so temperature rise may increase. To reduce that, we should improve the surface finish. If we are able to do it, there's a possibility we can utilize the grease lubrication, or maybe the better grease, or maybe synthetic grease, which has or maybe the grease with some sort of nano additives, which we will be learning in lecture 15 when we talk about nanotribology, where we use a lubricant with a nano additives, so that the results are more favorable and we can dissipate the heat much faster. So this 10 meters can be extended to 15 meters, and this lubricated bearing will be useful for that purpose. So this is what we say. Now we cannot reduce the C, we cannot reduce the CR clearance, and we are not able to utilize the grease lubricant. So what is the next option is that reduce the diameter. Again, many times bearings are designed from a general diameter, so reducing the diameter may turn out to be difficult, but reducing the bearing length is possible. So one thing we can do, we can reduce the bearing length. Here we use the word 70 mm as a bearing length. It can be 60 mm, it can be 55 mm. However, whenever we go and reducing the bearing length, whatever the groove, that also should reduce. It should not happen that 70 mm bearing, if I am reducing the 60 mm and the groove remains at 60 mm, then it will turn out to be the failure. So we, the groove which is a oil feed groove, needs to also reduce in the dimension. But best way is that go ahead with a thinner oil. Reason being, if I'm reducing the viscosity, if I'm reducing viscosity, I'm going to increase the eccentricity, I'm going to reduce the attitude angle. So this is a very sensitive parameter. We will consider in one of the slide effect of those reduction of the viscosity. Let's take a second case. Here the we are choosing slightly on the higher side the length, the so instead of 70 mm previous case, now 80 mm, but L by D ratio, we the diameter is we are keeping again same 100 mm in this case. Clearance has further increased compared to last time. Other properties are already been defined. In previous example, axle groove extended at 10 degree. In this case, we are extending to 18 degree. And then and the way in previous case, it was a 60 mm in the length. Here we are using 65 mm, which is a naturally lesser than the length of bearing. So again the results have been compared. One good thing is that eccentricity ratio has increased more than 0.5, so it is advisable now, but still attitude angle is the lower side, so again the problem comes. And another thing, in this case also velocity is more than 10 meter per second, and there may be a challenge of using a star lubrication or maybe it's a grease lubricated bearing. However, as I mentioned, if I improve the grease type, then there's a possibility that I can extend this value also. Again, the same suggestion in this case, we can reduce the bearing length instead of 80 mm to 70 mm, or reduce the diameter if possible, or go for the thinner oils. So these suggestions can help us in a bigger way. So what we see, another one, when we reduce the viscosity, when I'm using the go with a thinner oil, but making sure that transient case failures are not happening. So whatever we are discussing here is a steady state. This is steady state. It's not a transient. It's not a beginning. It's not an ending. So steady state performance can be improved using thinner oil, but what will happen in transient situation, then if there is no appropriate lubricant layer, then the wear out will occur, so failure will be observed. So to avoid that, we need to ensure that thin fluid film layer is established. Can be physical adsorption, chemical adsorption, which we have studied earlier. It should shield the tribo interface nowhere, and then protection by boundary lubrication is ensured. If it is done, then it makes much more sense. So when we are talking about the design, we are saying we can reduce the oil viscosity but ensure that boundary lubrication remains intact, particularly in transient situation when we are starting the bearing, or when we are starting the shaft and stopping the shaft. In transient situation, it is very necessary. Now I'll consider, I'll go further, because we have been talking about the bearing design, and whenever we talk about the design, optimization comes its own. That's a major issue, major we say advantage. But here we are talking about a new thing, which is what we call the Pareto optimal concept, or many times we say Pareto optimal front. This paper was published in 2004, and what is here we are saying that whenever we try to solve any problem, gear problem, bearing problem, seal problem, whichever, generally we consider the multi-functions. It's not a one function only. So in this situation, we are talking about minimizing temperature rise, minimizing oil feed flow, minimizing the power loss. The three functions in this case. However, whenever we are trying to solve these three functions or three multi-objective functions, then in this we require a weighting factor. What is the relative importance? What is the importance of the temperature rise versus feed flow? Is the temperature rise is more important compared to feed flow? Or what is the importance of feed flow versus a power loss? Is the power loss more important compared to feed flow? If all three are equally important, then I'll give weighting factor one third, and one third in this case. But if power loss becomes more important, maybe say 50% importance comes to the power loss, I'm choosing weighting factor one half, and remaining temperature rise and feed flow is the same. So 1 by 4, 1 by 4 or 0.25 can be. All weighting factor summation should be equal to 1. So this is a major understanding, or the main understanding from that. So what we did in this, we say that whenever we are talking about the optimization, many times because this variables are not continuous variables, and many optimization problems they we consider as a continuous variable. Now why I am bringing this optimization problem even in the lecture 10th itself, we have a total 36 lectures. Reason being, maybe lecture 18th onward, this optimization will come one way or another way. and all the machine learning algorithms, they have a penalty method. They have whenever we try to reach to the right solution, we use a optimization method. It can be gradient descent method, it can be more complicated method, it can be genetic algorithm. So it can be any optimization. So the we require optimization in almost all machine learning algorithms. That's why we are trying to bring here, so we have some understanding, and in a future lecture it will be much easier to cover those aspects. Now here one point, as I mentioned, that many times we have a discrete variables, we don't have a continuous variable, so conventional optimization technique may not be utilized. Another one is that we really, in our every optimization we have a constraints, so we need to bring those constraints. As I say that most of the machine learning algorithm, we have a penalty method. We give penalty to error and maximize the penalty so that we get a much faster convergence. So same method, we go ahead with optimization methods. We have a constraint. Now constraints can be maximum fluid film pressure like a 10 megapascal, 20 megapascal. We constraint may have a minimum plumb thickness constraint. It may be lesser than 5 micron. They should not be the thickness should not be lesser than 5 micron. Should not be lesser than 10 micron something. Or temperature rise. The temperature rise should not be more than 15 degrees centigrade, because we know that increase the temperature, viscosity changes significantly, and then quite possible ultra mild wear may turn out to be mild wear also. Sometimes we do have a the consideration of the critical speed. Sometimes when we operate the system and the operating speed is a more than its than the critical speed, then there is a possibility of the failure. So we really check also critical speed. Now, as I mentioned, we impose a penalty particularly on those solution which fail to meet the constraint. So this is important. In this case, we also use a three-level Taguchi approach to quantify the what will be the impact of the design variables. We use a Pareto optimal set, which will be demonstrating. I'll show in the next few slides. To separate, one thing is that what is a superior design vector. So we are saying the design is a one. We can calculate the design vectors using a numerical method, but which one is good, which one is the best, we should also think from that point of view. In this paper we solved the three examples to compare it. Now first one thing is that discrete variable. Now we say the oil viscosity is a discrete, it's not a continuous. You look at this one, ISO standard, ISO 2, viscosity minimum value is a 1.98 and maximum value 2.42. But after that we don't have continuation. Next viscosity is a 2.88. Then here the upper limit 3.52. Next viscosity is a 5.14. So we don't have in between values. Of course, we can change this value, increase the value by adding the nano additives. That's a possibility. But initially, when we are checking the selection, we really need to go through the discrete variables. And here particularly for this purpose, what we are saying, design factor which are affecting the bearing performance, radial clearance really is one of the very critical factor. Length is a factor. Sometimes we say diameter is also a factor when we are designing bearing and shaft diameter is not known. So we can calculate from a load point of view, but most of the shaft diameters are known. Viscosity is very critical, and then groove shape and the location where it will be located, this can be also optimized. And as I mentioned that oil viscosity is a discrete variable. Many times lesser than 1 micron film thickness constraint doesn't make much sense. We know that if I keep and the lesser than that, surface roughness will be issue, and then manufacturing will be majorly problem. Sometimes we also say that alpha d ratio, we need to keep in manner that alpha d ratio should not be lesser than this value. Of course, in my most of the cases, I keep alpha d ratio equal or greater than 0.2. Lesser than 0.2, I don't go ahead unless it's a very and then the micron level bearing, and there is essential requirement. We don't get into the lesser than 0.2. And then here we are saying that when why we are talking of the multi-objective, I can solve each objective separately. I can minimize the temperature separately, minimize of oil feed flow separately, minimize power loss separately. But major problem comes when you solve each objective separately. Every time design variable will be different. Which design variable you are going to choose? So that's why we need to choose a multi-objective optimization, and this will be common for the our future lecture also. Now, what is a multi-objective? For simplicity, I am choosing here the two objective. One delta T is a temperature rise. This is a oil flow. Now here we are multiplying with alpha 1 and beta 1, alpha 2 and beta 2. So this is a formulation of the problem. Now what is alpha 1 and alpha 2? They are weighting factor. In previous lecture, on the previous slide, I mentioned that three factors, and then the weight, summation of the weighting factor should be equal to 1. So in this case, if alpha 1 is zero point 0.1, naturally alpha 2 will turn out to be 0.9. Or alpha 2, in this case alpha 1 is a zero point 0.2, then alpha 2 will be 0.8. Or maybe sometime we say alpha 1 is a zero point 0.5, naturally alpha 2 will turn out to be 0.5. So this is just a summation of this. Now one major thing is a beta. Beta is a basically scaling factor. We are combining in one algebraic equation. We know the flow rate unit of course depends on unit, and the temperature rise, they are totally different unit, they are not same. So in this situation we need to scale multiply in the factor, so they do not affect each other. Otherwise what will happen, whichever is in a higher value, that will dominate to get minimized compared to the smaller value. So we need to scale up or scale down one factor or other factor. So this is very important. And now when you see each combination of weighting factor and scaling factor yields a distinct optimal friend. So this here the we are thinking about optimal friend. We see now if I know the alpha varies, I can go ahead with 0.1, 0.2, 0.3, 0.4, 0.5. I have a range. So if I go ahead with those factors, I'll come up with a series of a combination, and there we can go ahead with the Pareto optimal approach to evaluate all possible function offer inside. And how it will be done, I'll be covering in next slide. But major the thing will come, we can avoid that trade-off. Many times in optimization problem, people say, oh, trade-off, what is a trade-off? We are trading off, particularly giving more weightage to oil flow or lesser weightage to the temperature rise. So particularly in this case we don't have to think about trade-off. Once all the sets are available, all the data are available, we are approaching to the optimization. That time we can see what are additional constraints. If we are bringing constraint, then we'll get a one optimal solution. Or if we don't have a constraint, then we will come up with the market, what is the trend and what is it really available. So those things can be decided later. Initially we are not deciding anything, we are not going at the trade-off, we are trying to go ahead with a complete solution, so the results are available to us, so that we can take a decision on a later manner on this. So let's come with the bearing design. We say that and we showed one other design table. Of course I published design table for the static bearing, or maybe the and second paper on dynamic loaded bearing, but this will provide us some sort of formulas, and most of the time input is eccentricity ratio. And then we say that in lecture 9 or in this slide also earlier slides, that this bearing problem is an inverse problem. So we can guess initial eccentricity ratio, the first step eccentricity ratio, in this form. So here is the rotational speed, here is the viscosity, and then the diameter, this L by D ratio, clearance and applied load. Now we know very well this eccentricity ratio will not be accurate. It is just an assumption, initial guess. So we update this eccentricity ratio in every iteration. And what we do, how the iteration is being done, this is a kind of multiplier factor, so that we want to go ahead with slow pace, we don't want to go jumping in there. It can be 0.001, it can be 0.01 also. And this factor you can see here, we apply load, calculated force. If applied load is a more compared to the calculated force, naturally W by F will be more than 1. If it is a more than 1, then naturally eccentricity will go on increase side. However, if the W by F is a lesser than 1, and then this ratio will be the this bracket value will be negative. That means eccentricity will be decreased. So this way we iterate the eccentricity ratio, and in few iteration we come up with the right solution. And there's a in the Cowfoot method for wall speed onset, but they say that there's a critical speed, and we generally know that eccentricity should not be lesser than zero point 0.5. This can be calculated, and then we find okay, if it is a bit this onset velocity or wall velocity is on higher side, then there is no problem. If it is a lesser and operating speed is on the higher side, then we need to redesign the bearing. Another point, when we go for the optimization, we generally keep a lower range, upper range. Here in my most of the calculation, I kept a 1 millipascal second as a lower limit. It cannot be lesser than water viscosity, and then because it's oil viscosity, and then upper limit is 100 millipascal second. Reason being that we don't really require the more than 100 millipascal second. Now, lower bound on the clearance I kept as a 0.1%, but upper bound can be 0.5%. Reason being, in previous example we have seen the factor was something 1.57. That means, and then this was a 0.157 percentage. Another one, as I say, the length to diameter ratio, I keep generally in the range of zero point 0.2 to zero point 0.8, in this range only. Now coming to the Pareto optimal front, and as I mentioned that alpha, we can vary from 1 to 0 to 1 in a number of discrete steps, and then we can maintain some constraint, and this is all optimum solution. When you solve the problem, every solution is optimal solution, but we are able to see here we are trying to minimize the power loss, we are trying to minimize oil flow, and we want absolute value something over here. The whichever the point which are coming near to this side, that is a very good. Now here we know this point is far away, this point is far away, this point is far away, this point is also away, this point is far away, this point is also away. So that's why we say that these are the inferior points. So what we say, point A1, A10, 11, 12, 9, 8 are considered inferior, even though these points are optimum point because of the different weighting factor. But these are the inferior point compared to other points. While say the A2, which is coming here, A3, A4, A5, A6, A7, they are the superior points. So when we make a friend, we can take a decision later. So initially we don't have to, before we start our problem, we don't have to consider. We need to get some results, and then based on that we need to think about that. Now here, as I say that bearing case, we are trying to reduce the viscosity many times. So we need to really keep a restriction when you are solving the problem, either on the fluid film pressure. We know that when eccentricity increases to significant level, the pressure increases exponentially. Similarly, the temperature also increases. So we keep a limit on the fluid film pressure, temperature rise, and also the limit on the film thickness. So there are three criteria. It also ensures that two surfaces will not touch, and then they will not be anywhere. Now here, to really we can consider number of variables. For the simple case, we can consider radial clearance one factor, lubricant viscosity second factor, L by D ratio third factor, and then we also use L27 orthogonal array for the when doing experiment, or at least doing analytical experiments. This detail will be shared in the lecture 19. The topic of the lecture 19 itself is experimental design and statistical analysis. So here a statistical analysis is really required. So that will be covered in lecture 19. For time being, we are just going to share only the results and how do we judge or design, think from design point of view. So this is what we are showing, table 3, comparison of optimum results for the various objective functions. You can see here load situation 1, load situation 2, load situation 3, operating situation, and here we are including the Pmax as one of the criteria, the constraint. This is fifth, of course load situation may be same, but objective function has been changed. Here objective function again is has come same, but with a other consideration. Everywhere we are putting P max as a criteria. If you see in this table, whenever we have a temperature rise to be minimized, oil viscosity is coming down, and where the minimum flow oil flow, then here the viscosity is increasing. That means if and then the oil flow will come down only when there is a higher viscosity. Again, when temperature need to be minimized, of course in this case we are combining, we are saying the minimum temperature and minimum oil flow. So this is a basically optimization or multi-objective optimization. So this portion is a multi-objective optimization or two objective optimization, right? And then you can see the results are slightly different. But one of the major issue comes with the power loss. So you look at the power loss is a huge. That means this is not satisfying, or maybe when you're choosing only two factors, the power loss is increasing significantly. That is cannot be sustained, or maybe cannot be say it is not appropriate design to this kind of thing. And another thing, what we say that the mostly p maximum is kept at the 10 maximum. So the wherever you can see the value is 9.98, 9.9, 9.6 something. If we relax it, then the solution will be slightly different. And this is basically, you can see another thing, whenever we are going for minimum temperature rise, we are getting maximum clearance. Clearance should be increased because flow rate will increase. However, when we are talking about the minimum oil flow, the clearance come almost on the lower side. When we are combining multi-objective, then the clearance comes in between somewhere. So we really need to see from that angle what is the impact of the each parameter, or maybe say when you see we are talking about the optimization of, with respect to only minimum temperature rise, then the parameters are totally different. When you are talking only for minimum oil flow, then parameters are different. We're talking about the multi-objective, the parameters are different. So this is a very important aspect to keep in mind. And then here particularly said in this case we use a 10:4 as a scaling factor for oil flow, and we have given weightage as a 50-50 per this results. Now coming to the how do we really select which objective function is it correct. In previous slide we say that objective function power loss was not selected, it was only the oil flow and the temperature minimization. So these two objectives were selected, power loss was not selected. So how do we really go with the right objective function? So I'm writing back the same thing, temperature rise and oil flow. Now we are saying the temperature rise itself depends on the power loss, and then if you substitute this in power loss term, what we get here is something like first term for the temperature rise, second term for the oil flow. When we see carefully, what are we doing? This power the oil flow comes in denominator and this comes in a numerator. So this is a very important aspect. What we are writing here, increase in a temperature is determined by amount of power loss and occurrence of oil leakage. To minimum temperature rise, it's in a imperative, it's necessary to minimize power dissipation and maximize oil flow. That's what has been shown here. So what, in the other words, even we are writing a combination of the function, a multi-objective optimization. Here we are trying to maximize the oil flow and minimize the oil flow. This is a two contradictory thing which we are doing, which is not correct. And this is what really need to be identified. Whenever there is an objective function which we are considering, they should not be dependent on each other. Here the temperature rise is dependent on the power loss and oil flow. So if temperature rise is depending on the oil flow and I'm trying to optimize simultaneously, naturally this results will be absolutely wrong results. So we should not do that. That's why we are writing here, optimizing a weighted combination of power loss and oil flow is a superior objective function compared to optimizing a weighted combination of temperature rise and oil flow. Reason being, temperature rise itself involves oil flow, and lesser the oil flow, more will be temperature rise. So if I'm trying to minimize, actually I'm maximizing oil flow, and in one problem I'm solving minimizing oil flow as well as maximizing oil flow, naturally, which is a contradictory, and we need to understand this properly. And one more thing comes, so sometimes we choose a oil viscosity slightly on a higher side, reason being what we say that they have a self compensating behavior. If temperature rises, increases to this maybe say 1 or 2 degree extra, what will happen? The viscosity will come down. So it will compensate its own, and that's why we use a word oil viscosity many times go ahead with the self-compensating behavior. So slightly on higher viscosity is also acceptable to us. Now coming to the the power loss, instead of power loss we use a coefficient of friction as one of the objective function here. Now and oil flow is another factor, and we have selected all and the optimized solution. You can see these are the inferior solution 0.0073, 0.0112. These are all inferior solutions. Now if we separate, and we know that in this zone only we are getting superior solutions. So this is at optimal front. This is what we say Pareto optimal front is this one. So whatever the solution which are coming on this, we need to discuss on those solutions. That means when management takes a decision on the bearing selection or the choice, they can select this as a optimal front. Now if I'm bringing here in a tabular form, you can see coefficient of friction, the 7 value which has been shown over here, oil flow values, radial clearance, L by D ratio. Now when you bring this to the management, decision is much faster, much easier. Now what is the oil viscosity we are keeping as a 1 millipascal second, 2 millipascal second, 5 millipascal second. So we don't have much significant variation in oil viscosity. Radial clearance also we are keeping something like 40, 42, 43, and we know that there is a statistical variation itself. If I want to intend I want to maintain a 40 micron as a radial clearance when the bearing is manufactured, quite possible plus minus 2 will come. That means if I choose here the 42 as a micron clearance, it will go plus minus 2. Naturally, then it can be 40 to 40. I don't have a much say on this. So even though when we are going for optimal front, whatever solution coming, it also gives a reliability to us that if even there is a fluctuation, a statistical fluctuation, what will be the overall result, whether it will be favorable or not. Now what has been interpreted in this, say most significant factor is viscosity, which is influencing the power loss, the coefficient of friction. Clearance has a most significant impact on oil leakage. Oil flow clearance plays more important role, and then viscosity plays second role. Coming to the L by D ratio, it doesn't have a much significant impact, it has a moderate impact. We look at the 0.55, 0.83, 0.64. So even if I now choose a zero point 0.6 as a 1 by L by D ratio or zero point 0.5, it's not going to vary significantly. So this kind of analysis really helps us to understand which factors are more sensitive, which factors are less sensitive. So we work on this. So this is one of the machine learning algorithm, what we call the PCA, can also be utilized for this purpose to understand which one is better and which parameter will really influence a lot, and where we really require close tolerance and where we require lesser tolerance. These are the important aspects. With this I say thank you for attending this lecture.